Okay. So let's share my screen. So that's about the substation, classification of substations. Now, now we selected the voltage. So what is the voltage level? I have to step up the 33 kV voltage to 220 kV voltage. So voltage levels are fixed. My incoming voltage to my substation is 33 kV and the output is 220 kV. So the 33 kV incoming is coming from my wind farm. This is my 33 kV incoming, which I am stepping up this 33 kV to 220 kV, and this 220 kV is connecting to the grid. This is my general idea of my project. So we have to do the design for this portion, the substation primarily. So now in this, so to start this work, I have to select the substation location, right? Which location is a good for me with respect to some points. I have to consider, oh, this is a good location for my project. So what are the things we have to consider when you are selecting the substation location? See, this is suppose we awarded the project in one location, and if I send you all you guys to that location, and if I ask you to select the substation location for our project, then what are the things you will check at the site? Let's see those. So obviously, the substation site evaluation to be done in two things. One is the technical, other one is the economical. Whenever the design at any stage of the design, when you are selecting any equipment, any bolt, wrench, small washer, you have to select in a fashion of technical evaluation and an economical evaluation, because you have to bring out a solution that should be commercially viable. It should be technically, it should satisfy me, and commercially also it should satisfy me. So you have to select that as an option. Let's see that. Let's first talk about the technical evaluation, and then we will come to the economical evaluation. Let's go to the technical evaluation. So first of all, what are the things you will check in the substation? If I sent you, first of all, you are selecting you are checking that the land, choose areas that minimize the need for earth movement and soil disposal. Why this statement has come? Because tomorrow, if you are having all the trees and there is no certain level of the land, or some holes, or it's like a highly plateau land, no plain land, then you have to bring all in the same level. It will cost you more. It's an additional cost to you for earth movement and soil disposal. So try to choose the land that minimize these works. Next one, the water. Avoid interference with the natural drainage network. That's very important. Third one, which is the vegetation. Choose low productivity farming areas or uncultivated land. Fifth one, protected areas. Avoid any areas or spots listed as a protected areas, like near to the airports, near to the railway stations. No. Avoid those areas. Near to the in the forest areas. Try to avoid those locations. Community planning. Avoid urban areas. Land cost is very, very high in the urban areas. Development land or land held in reserve for future development. Avoid those things. Forest areas or the land near to these river crossings or near to the railway crossings. Avoid dust. And engage. Yes, land in urban areas is high, right? If you compare to the rural. See, we need, if I'm, yes, okay. Community involvement. Just engage nearby community, all the people in the approval process. So we can get a clearance, like a no objection for constructing the substation. That is a very, very important thing. And the next one, topography, as I said before, that should be flat, but not prone to the flood or water stagnation. Let's check other surrounding areas. If all towards the all the places is hilly areas, sorry. If all the surrounding places are hilly areas, try to avoid those middle one, because the water during the rainy season, the all the hill water will come down to your substation. Whole flood or water will be stagnated over there. Try to avoid those. Let's check what is the flood levels or flood in that area. Check that. Yes. And soil suitable for, select the soil that should be suitable for construction of roads and foundations. And low soil resistivity is a good option. Why? In the soil, low, if you are having a low soil having a low soil resistivity, then it is easy for you. It is easy for you to do the earthing design. Earthing design will be easy for you to do. And also the civil constructions. If it is a highly rocky area, to construct, to lay the foundations, you have to do the pile foundations. It's costly more again. So select the soil having a low resistivity soil. Very, very important for our earthing design mainly. Access. Try to see that location is having a easy access for transportation, because we are having a large equipments like breakers or transformers. So, and operators and maintenance teams. Check the road access. If not, let's see what would be the cost if we lay the road from the existing road to our substation. Line entries. Check that where the line, now the 220 kV lines in my substation has to go out. So how the lines will go out? And check the line corridors. Will it good for, if I select this, how my line should go? If I'm selecting, suppose, my location, let's see, this is my area. Now I selected a substation E here, and this is totally a forest area. Okay, a forest area. Now my grid substation is here. My grid substation is here. So the 220 kV lines obviously has to cross through this forest. If you're crossing through the forest, if the line is crossing through this forest, what it will cost you more. Because cost you more, and again it's a very difficult to get the approvals from the central forest clearances. Very, very challenging thing. So then you have to shift this orientation little bit. Then you have to take the 220 kV towers in this way. Let's check that whether there is a scope for taking out the 220 kV lines like this. Suppose if some other lines are going here, existing lines, then you have to again cross this. So at what distance it is there? If it is very near, you cannot cross. Again, you have to go like this. So if you are having those constraints, let's drop here, go to the other place, maybe here. Even though line length is coming more, no, there is no option for you. So select in that way. And the last one is the pollution. Risk of the equipment failure, maintenance cost increase with pollution level. Like if you are doing this project in coastal areas, there is a mention of salinity, salt, and the dust will just accumulated in on your insulators, and that the electric strength of the insulators will lost. So it's create a arc formation between the face to the ground. the insulator will burst, creating a fault. So try to check the pollution levels in that area too. So these are the main important considerations you have to check when you are selecting the substation location. And again, second one, economic evaluation. Here, economic evaluation, the evaluation should address the level of affordability, return on investment, initial capital cost, and life cycle cost. So how to compare this both and bring the solution? Let's see. I'm taking a small example here. I am having a one land here. I am having one more land here. Suppose this land is having a good soil and it is good for my civil constructions or all thing. So what the cost of this land is, suppose a 10 crore rupees. Okay, 10 crores. Now, other project, this is the one more line. Sorry, this is the one more land, which is a highly rocky area. Raw soil resistivity is very, very low. Sorry, very, very high. And civil foundations, you have to go for a pile foundations. So it's costly. The civil works is also very, very costly here. But this lands cost me only 5 crores. Because a waste land. So what I will select, whether the 10 crores one or 5 crores. Then I am doing a rough calculation of earthing on this. What would be the cost if I am designing earthing here? And what would be the cost here? And as well as the civil things. And if I am checking, the earthing cost me for this project is 1 crore and civil cost is 3 crores. So total 4 crores. So the investment is 14 crores here. And here, if it is twice, 2 crores for the earthing and 6 crores for the civil, then it's cost me 6, 7, 8 plus 13 crores here. Here in the rocky area, I am saving 1 crore rupees. So obviously I will go with rocky area only instead of low resistivity soil. So that is the that I am checking with respect to the economical. So always, not only in this, in the line entries on the when you are changing the line, what would be the cost? That all these things you have to do compare as a design engineer, and you have to bring a good solution that should be again a techno commercially viable one. Understood, team? Am I clear till now? Any doubts you can ask. See, what if you yes, sir. The investment in the low resistivity is 14 crore rupees. If I am going with a land of rocky area, my investment is only 13 crores. I am saving 1 crore rupees, right? Yes, that is I'm saving 1 crore in the project. That is a rough calculation, what I mentioned in a simple way. Yes. So Ankit, what's your doubt? Please drop here. Others, all understood the concept?
Sir, hello.
Yeah, please.
सर एक्चुअली आई एम बीच में से मैंने क्लास ज्वाइन किया, सो इसीलिए मैं थोड़ा रिपीट के लिए बोल रहा था सर.
Okay, fine. So I am talking about it with the technical substation location selection. The substation location selections we are doing with respect to the technical evaluation and also the economical evaluation. So in the technical evaluation, these are the things we have to consider, we have to look, and as well as again subject to some conditions. So what is that? The economical evaluation. I am checking the some criteria regarding the investment in capital cost and life cycle cost or in return on investment. So if I am comparing the both the technical evaluation with the economical evaluation, and I have to bring out the a good solution that should be beneficial with respect to the both technically as well as the economically. That
Okay,
is
sir.
my
Okay.
point. Yeah. Application of earthing for both sides is not as easy as it needs to measurement of soil properties, right? Is there any thumb rule for such? Yes. See, generally for the earthing design, we already, so team, please mute your mics if you are not talking. Yes. See, already we developed the earthing design for our project. Sorry, before the previous projects. In the earthing design, what is the main important factor influencing here? One is one is the soil resistivity, other one is your area. So already we are having the design and we are having the area. So when we change that area parameters and when we change the soil resistivity, then we will come with the bill of material required for our earthing. That already in every developer, at every developer, they are having the standard sheets. I'm also having that we are discussing in when at the time of earthing calculation. So from that bill of material, so this is not a simple exercise. What I have done, it will take some 2 to 3 days to do this activity, team. We are doing some a rough work on this. So we are designing the earthing for both, because we all suppose now if you ask me, I will come to know that suppose, oh, for 33 by 220 kV, in 33 kV how much equipments will become. So the lightning arrestor, all these things. So already having a table in the Excel, I already prepared one table. In that, oh, for the lightning arrestor, what are the flats to be laid? 100 into 16 mm, 50 into 8, and 75 into 12 for 220 kV. Fine. And for the breaker, what are the earthing points required and what is the length? And down the earth mat, what is the earth mat for 33 by 220 kV system? 75 into 8. So how many lines will come? If my area, by selecting the area, if I am adding that formula, I will get the total earth mat there. And I am calculating, this is the weight of my total GI, galvanized iron flat. So I am calculating that. So same for the high resistivity. What is the additional things I have to do? I have whether I have to increase the area, or whether I have to reduce the spacing between the things, or whether I have to lay the electrodes. These are the some other things we are tuning to gain the get the accurate means desired results of touch and step potentials in the earthing design. So we already developed these things in Excel sheets. We are already having the standard sheets for this. So just when we are adding the soil resistivity and area, we will get the entire BOQ for the everything. I hope I cleared your point. Yes. Fine. So others, any doubts here up to here? Shall I move? Okay. Let's see. So we selected the substation location, and now we have to select the grid substation. To do this selection, we have to do the load flow studies, short circuit studies, and contingency analysis team. These three things we are discussing in the ETAPS in our next classes, but I want to give a brief idea of this in this class before concluding today's session. Let's see, just give me time for another half an hour. Let's see. Suppose now I selected the substation location this. This is my A33 bar 220 kV substation, right? 33 bar 220 kV substation. Okay, so before going to this, I want to tell you one concept which is about the short circuit levels team. Short circuit levels. This is also very other important factor need to be known before doing this grid substation selection. So every substation could be a LV substation, MV substation, HV substation, or extra EHV or UHV, all the substations having some short circuit levels. What is meant by short circuit level? Just in a simple way, for easy understanding, I will explain you a small story. Let's see. In the year of 1974, maybe let's assume. Just I'm telling you a story. Here in this year, this is the area we are having a 4 generators, and these 4 generators are generating. These are the 4 generators working on the coal, the thermal power plant, and these generators are supplying power to that town and industries as well. And these are all interconnected to a substation. These are all interconnected to a substation. And this substation is feeding to all other substations which are near this is a substation in the center, and from this substation it is distributing to all other distribution substations. From here the supply is extended to all the houses and industries as well. Now one fine day a fault has occurred in the substation. When a fault occurred in the substation, so what are the fault contributors? One is all my induction machines, synchronous machines, generators will feeding the fault. So these generators are feeding the fault to the substation. This is the fault, this is the fault, this is the contribution of this generator, and this is the contribution of this generator. And based on this MVA and subtransient reactance, I calculated what would be the chance of delivery of the fault current from this generator, and the power system engineers already calculated this, and they found that the maximum fault occurred in this substation is 4 kA. I mean, all the generators are feeding 1 kiloamp of current to this substation. Suppose let's assume this is a 220 kV substation. 220 kV substation. The fault current is 4 kA in the year of 1974. After, due to the population rise and urbanization, the substations, there is a huge demand. So some other parties also came into the system by adding some generators. Now, in the 1974, the fault level is 4 kA. So, whenever a fault occurs, we have to open the breaker. But we are considering first condition, and we assume that all the equipments should withstand for 4 kA per 1 second. It is some safety condition for all the equipments. Could be a conductor, transformer, everything. I am asking the manufacturer my fault level in my substation is 4 kA. So please design all the equipments offering to us that should be withstand for 4 kiloamps per 1 second. So manufacturer designed with respect to this condition, and he type tested with the laboratories, and he delivered the product to us. Now, I am fine with this. In the 1980, by addition of 2 generators, now the fault level rised to 6 kiloamps. 6 kiloamps. Sorry. What is the minimum factor required for this 4K thing? The minimum factor, see, this is an example I'm telling. So this 4K is coming from the generators. So the factor which is influencing here for the 4K is fault level, fault current are different. Let me clear first Mr. Muhammad question. See, the 4K depends upon the factors. One is your line impedance, other one is your subtransient reactance offered by the generator, and also your generator rating as well as the voltage rating. Fine. So those are the factors affecting factors influencing on this 4K. This is an example I'm telling. Now the fault level and the fault current are same terminology. Fault level generally we will represent with respect to power, like MVASC. Similar, if you just take the voltage of 220 kV and if you calculate the power with respect to the fault level, like root 3 into 220 kV into 4 kiloamps, then you will result with the MVA, short circuit MVA, which is the fault level. Fault current is 4 kV. Clear? Okay. So in 1980s, by addition of 2 generators, the fault level is raised to 6 kA. Now, all the equipments are designed for 4 kA. Now, they can't withstand for 6 kA for 1 second. So, what I decided is, I decided to replace all these equipments with 4K, with 6 kA. And he done that. Similarly, going on. So every time I'm replacing this. So to avoid these things, the power system engineers across the global, as per IEEE or IEC, they standardized some fault levels with respect to the voltage level. It seems for 33 kV, they standardized the fault level with 25 kiloamps for 33 kV. Let's share you that. If you see here, for 33 kV, they standardized for 25 kA, and for 132 kV, 31.5 kA, 220 kV, 40 kA, 400 kV, 50 kA or 63 kA, 765 kV, 40 kA or 50 kA. These are the standardized fault levels for that substation, for the voltage levels. Yes. Again, it is as per IEC. Yes, it's as per IEC. But again, you can find the voltage level. Again, you can see the short circuit levels or short circuit current fault levels. For 132 kV, you are having 40 kA also in the market. In 220 kV, you are having a design of 50 kA also. You are having the designs. And also, it is a competition in the manufacturer. And these generally, as per IEC, they are saying that all these should be designed for 1 second. But as per this manufacturer competency, when they are doing the type test, they noticed that those equipments are withstanding 40 kiloamps for 3 seconds. So what they are doing, they are marketing. They are doing the marketing promotions like, oh, my breaker can withstand 40 kA for 3 seconds. Obviously, you required only 1 second because the last node of the breaker will trip at 1 second in the worst condition. What happened? That's the worst thing. But this is some promotion or kind of marketing techniques using by the manufacturers. So now you can ask me a question that suppose if the 40 kA, if in the 220 kV the fault current is raised beyond the 40 kA, then what would be the solution? Then you have to go for the like I mentioned, these are the some additional things, some mitigation techniques. Like you can go for a splitting of a bus if you are combining the bus, suppose, or you can use a series reactor or fault current limiter. Now I have seen latest technology, which is a superconducting fault current limiter, SFCL. That is the one thing. Or the the transformers also reduce the short circuit levels, because the impedance offering by the transformer will reduce the short circuit levels. You have to go with these things. If it is more than that, fine. So let's again come back to here. In the if you go for the higher system voltage, network is very low, so the fault levels is only 40k or 50k. You can see mostly in 400 kV and 220 kV. So those are having a 50k and 63k. In 765 kV, the network is less, and also the conductors you are laying in the 765 kV with respect to the withstand capacity of the short circuit, the cross-sectional area is very, very high. And you're laying the bundled conductors, big conductors, and they are traveling for kilometers. So the impedances of the line is also giving some additional advantage on the short circuit conditions. Mainly on the network. How the vast is the network? 400 kV, you can see the network is vast. 765 kV substations, you can see rarely, right? 220 kV, mostly you can see 220 kV substations and 400 kV substations compared to the 765 kV. That is the one reason. Fine. So let me share you again, go to this. So now I selected a substation. This is my substation. This is my a 33 bar 220 kV substation. So from this substation, I connected to, I am having a different grid substation near to this. A, B, C, D, E, F substations. Suppose a substation is 132 kV bar 400 kV substation. B substation is 220 bar 400 kV substation. C 220 kV substation, which is a 16 substation. 400 220, it is also a 220 bar 400 bar 765 kV substation. This is 220 bar 132 bar 33 kV substation. And this is a 220 kV bar 33 kV bar 11 kV substation. Suppose, let's assume. And these are all the substations located from this in this way. This is a substation locating at 5 kilometers, suppose 1 kilometer, 2 kilometers, 3 kilometers, 4, 5, and 6. So when I ask you to which substation you will go and connect. So first what you will decide, you will say select which is the less length. So obviously one is 1 kilometer, which is very less. So I can save the line cost, conductor cost. But if you see here, 132 by 400 kV, there is a no 220 kV. How will you integrate the 220 kV here? So this substation is ruled out for our project. Then I am moving to the next second substation. I went here and I find there 220 kV is there. But here what I noticed is the 220 bar 400 kV, where the 220 existing 220 kV, which is stepping to 400 kV, the transformer capacities are already highly loaded. So you're not, the transformer is only 300 MVA transformer. Out of 300, already 200 MVA is loaded. Only 100 MVA is left. But our project is 200 MVA. So the transformers loading issue is there here. You cannot export 220 to 400 if you connect here. So transformer loading. And if I go to the substation, Here it is a 220 kV substation, only line incomings and line outgoings. The line incomings, if you, there is a, I am checking whether there is a space is there in the substation or not for integrating your power. So what I am checking the space. I found there is no space in the substation. So I am checking the next condition, space. I went to the substation. I find the space. I find the transformer loadings. But here, the 400 kV lines are highly loaded. If one of the line is failed, at that time, I have to shut down my system. Other line cannot able to carry much of power. So the line loadabilities I am checking. And so I went to the substation. Here in this substation, I have checked all the conditions are satisfied, but the existing fault level in the 220 kV is already 38 kA. When I'm coming and integrating to this substation, the fault level from my substation is contributing. If a fault occurred in the substation, the generators from my side is also contributing the fault, which is suppose a 6 kA, which is crossing the limits of 40 kA. So I avoided this also. So finally, I am going and connecting with last substation, even though it is having a higher having a line length is more. So what are the conditions I'm checking? I'm checking whether there is a voltage applicable is there or not. Whether the transformers are loaded or not. What is the loading availabilities of the transformers and the lines? And what is the short circuit levels in that substation? Whether the space is there or not. So the loadings, the transformer loadings and line loadings, how we will know? How can you measure? So this will get from the load flow studies. And how can you know the short circuit levels? This you will come with the solution from the short circuit analysis. So these two studies we will perform, and actually this is the substation I am connecting to some grid. Obviously, we are not having the entire Indian grid, southern grid data with us. So these activities in-house we are not doing. In every company, we are giving this system designing to the third-party agencies. Like in India, you can see PRDC, Power Research Development Center, which is located in the Bengaluru, and Siemens is also having the softwares, and they are having the data, not software. They are having the data of the grid. So they are having the data that in the year of 2023 to 24, what are the projects are coming, and what would be the constraints if you are connecting to the substation by that new coming lines. So everything they will do, and they will generate a report to you. So based on the report, you will take a decision. And this report also we have to submit to the bank to get the loans for your project. This is a mandatory. Bank definitely will ask you to submit the PRDC or these reports to sanction the loan for your project.